And once again, welcome back to the class. So this video we are continuing, and you'll be happy to know this is the last video in our series of magnetism and electricity. And specifically this time we're dealing with household circuits. I think the last video we actually literally looked at this, and this is literally the entire power grid that we see up here. And I just like starting each video out with a short review just to make it easier for you to test on these kind of things later. This entire thing is the power grid, and so we talked about the use of the transformers and either stepping up the potential or bringing it down. And the last one was this bringing down the potential and bringing it literally into your home. So literally that's where we're starting out today, is with like a little bit about like what's going on inside of your house. And so this is typically the wiring inside your house. You're going to see something akin to what you see here: a black wire, a white wire, and probably a bare copper ground wire inside there. Some of the wires you'll notice like have a three-way, like this wire has a red wire in it. And we usually use those for what's known as a three-way switch. And if you're sitting here going, Mr. Cole, I have no idea what a three-way switch is. Yes, you do. If you've got a room in your house, let's say that there is a light in the center of the ceiling. Dun, dun, dun. That's a terrible light, but anyway. And you've got a switch on both sides of the room, so you can literally walk in one door and turn the light on, walk out the other door and turn the light off. That's a three-way switch. And so in order to wire that up, you've got to have this red wire in there. But anyway, now that you're learning how to become an electrician, we can move on. But typically you've got like this two-wire configuration here. The bare copper wire, that's actually just for safety. It's kind of funny. It and the neutral are actually connected together anyway. And so like the only hot wire, say for example in a normal household circuit, would be, if it's wired correctly, that one black wire. If we were in class right now, one of the things I would probably do at this point is walk over to an electrical outlet, and before class, I would have already taken a meter and I would have checked to make sure which of the three prongs was hot. And usually I'll get everybody's attention because I'll take a paper clip and I'll put it into one of the outlets that there's no potential on. Well, obviously, unless you know exactly what you're doing, please do not put anything in light sockets. But it's usually a trick I play because I've already checked it out, and I know which one is actually the hot over on the wall. Now, if you're looking at a 220 outlet, like they can be pretty weird looking, like they've got weird shapes, just to make sure that you don't plug anything weird into the 220. What's interesting about them is they actually have one that's basically a positive 120 and another one we can consider like a negative 120 over there. So with those, yeah, you'll have two hots over there. So it's not a single wire that's actually like 220 volts, but you've got literally 220 volts, 240 volts, 210 volts difference between them. But I'll just throw this while I'm at it. Just out of curiosity, you'll notice that like there's different sizes of wire. And so that depends on like how much electricity, how much current you're going to be pulling through that wire. The more current you're pulling, the heavier wire you need. Otherwise, the wires will get hot. You can even melt the wires or set them on fire. So typical like electrical plugins are like a 12 gauge, and whereas your lighting may only be a 14 gauge wire, just because you don't have to have as heavy of a wire for your lights. This is a basic. Here's your breaker box inside your house. We'll talk about the breakers in 1 second so you kind of know what they're for. And you can see how this is a basic wiring diagram of like some electrical outlets and some light switches wired together in circuits. And you can kind of see how they're laid out with each other there, which I think is kind of important for you to have a little basic idea of what's going on. Although, unlike this picture, most people usually don't have lights and electrical outlets on the same line. I guess some people do. I would prefer not to do that. I like keeping them on two different circuits. But anyway, that's just me. Let's see what we got next in our notes. A short circuit, and we've all probably been around the short circuit before. I remember as a kid, I found an old drill out on the back porch of somebody's house that was abandoned, and I immediately brought it home, plugged it in the outlet, and the drill basically went up in a blaze of glory, but luckily did not burn our house down, but it did flip the breakers and all that, and I had to learn at an early age that was stupid. So a short circuit is when you literally have an unintended path takes place. So the circuit is literally shorter than it's supposed to be. And so you can see like here this wire that's been burned up some way inside this little box. I pulled those pictures off the internet. The Grand Cathedral that burned down like literally a year before this was made. What was interesting about it is it was probably, I think, caused because of a short circuit in a wire. So you can imagine two wires got too close. The electricity, it got too hot. Usually when you have a short circuit, the wires get hot, and that's when you actually see like the fire take place. In terms of you becoming a short circuit, which literally you can be the short circuit, it doesn't take a whole lot of amps to actually cause you. Now, I've been electrocuted before, and it's not a pleasant experience. I think the big thing is this. We see it as literally as small as just 0.2 amps. So an electrical current as small as 0.2 amps can actually cause your heart to stop and can cause burning. Let's see, without resistance, a wire carries more current than intended, and that's why we have ground wires. And the goal is to try and absorb that current so that it doesn't go through you. And overload. Now, this is interesting. I love this picture from the movie Christmas Vacation. And you see like that huge mass. I hope everybody knows in real life that's a terrible idea. Because what happens is like at your wall outlet. Like, let's see. Here's your wall outlet. There's your two plugs at the wall outlet. Usually that breaker is probably set anywhere from 15 to 20 amps. And that's because the diameter of the wire going to that outlet is maybe only meant to carry at the top end 20 amps perfect. What happens is if you have too much flowing, you will literally then melt the insulation off the wire, and you will literally set the wire on fire is what will happen. And so trying to pull too much, for example, in your house, maybe you've got a microwave, and I know at my house, if you turn on the microwave, and I've gotten like an industrial waffle maker because I really like waffles. If you turn on the microwave and the waffle maker at the same time, you will flip, i.e. our next section, the safety device. In my case, it is the circuit breaker. So that's why we've got these devices in our house. You've either got, now if you've got a really old house, I doubt many people have one of these anymore. That's actually called a fuse box. And literally a fuse, let's look at another example. Here's a more modern type of fuse. And if you look, it's two pieces of metal. Cars used to specifically use these, but other things do too. And you'll notice there's a very small piece of metal in that piece of glass. And what happens is it's rated at a certain amperage. So maybe like a 2 amp circuit or a 2 amp fuse. If more than 2 amps flows through that wire, the wire melts in half and it kills the circuit, and that protects your circuit. Old houses had fuses that were these round screw-in type fuses. People would routinely burn their fuses from overloading, and then they would actually take and place a penny in there and then screw the fuse back in on top of it. The problem is if you're blowing a fuse, that means you're overloading it. And so now if you've got a solid penny in there, you're now going to set your house on fire. So more modern than the fuse in the home is a circuit breaker. And they're usually made with either a bimetallic strip or literally an electromagnet inside. So literally you can imagine that as the amount of current going through the breaker gets stronger and stronger, at some point there's a spring and it literally resets and it pulls the breaker off. Now, the good thing about breaker compared to a fuse is with a fuse, you've got to actually have new fuses around. With the breaker, you can just flip the switch like that one's off you can flip it back on again. But again, if you're routinely flipping the breaker, that means you've got too much plugged into your circuit. And then we talked about this in one of our very earliest videos. It takes advantage of what's known as Lenz's law, which is incredibly hard to describe. But that's a GFCI, ground fault circuit interrupter. That's right, ground fault circuit interrupter. And it actually uses Lenz's law. And what's cool about this is it actually is set to trip before you even know that you felt a shock. So that's what's really cool about the GFCI outlets. It's also why that they're like required by code to be in bathrooms, science labs, anywhere you've got water nearby, because water is a conductor, and so it's a very easy place to get shorted. 10 minutes in this video, and I think we are literally at the very last screen here. Boom. And we're done. Just a little blurb about electronics. I had it in our review material, so I didn't want to leave it out. But specifically this concept of what an analog signal is and what a digital signal is, it's kind of funny. We live in a, people will usually say, digital age now. But I'm kind of a bit of a music buff. And what's funny is everybody is definitely more into music on an analog system. Even though recording studios are all digital, the reason why now is it's just easier to use software to manipulate sounds. You can make me sound like anybody by using digital recording methods. Old analog signals work literally because you can think about the guitar literally made like this completely variable signal that was transformed from an amp to another amp to your speaker, and literally you kept this entire analog signal. In other words, there is an infinite number of curves and little loop-de-loops here. In other words, imagine the strings vibration you're literally seeing in this analog signal. Wow. And like my voice right now, my voice is analog, which means my voice is or maybe high and squeaky, and that's crazy. But that's how my voice would look through an analog signal via wire. The problem is, you should be thinking, well, that's beautiful, man. That's like, sorry, I'm getting my hippie 1969 mode voice out. That's like beautiful, dude. That's like true voice, man. Well, yeah, you're right. The problem is it's just very easy for static, or what we call noise, to get into the signal, and then you've got other little signals in there, and it's easy to get interference in there as well. Digital speaker or digital signals, on the other hand, it all goes back to binary code. It all goes back to binary code. Hopefully, and I'm not going to go into a big definition of what binary is, but basic binary we can think of like is 8-bit binary code, where you can say, for example, transform, put letters in here. I once had a physics team. Our physics shirts actually one year was this huge mass of binary code, and one of our schools that was our competitors, they always wore flannel shirts to competition. So we had t-shirts made, we wore to the competition that in 8-bit binary read, "We don't fear flannel." So anyway, kind of a neat little gig to get in there. The cool thing about the digital signal, though, it being all zeros and ones, like, look at this analog signal. You can see the noise that gets in there. There's no noise in the digital signal. Remember, digital works by basically like a switch. You're either on or you're off. And so we can transmit that via fiber optics, like the flashes of light, and it's just amazing what we're able to do with digital signals. It's just, for a purist, it's just not the same, though. So that's why you see like vinyl records and things like that coming back into style now, because a vinyl record is literally this original analog. Yeah, you get the noise, but you're actually hearing, to me, the real sound. Sorry, I'm going to get like a weirdo if I keep going on about this stuff. But anyway, we live in a digital age, and computers speak binary code, so I guess we better as well. So anyway, we'll talk to you later. Ooh, I just got to thinking about, you ever watched the movie The Matrix? You really got to look in this digital world. Anyway, I'm shutting up. Later. This finishes the video series. Good luck with everything. Deuces.